In case no one warned you, this talk is in English. I will try to go a little slowly. If I'm going too fast, you can put your hands up like this, and I'll try and slow down. But good morning and welcome. And today we're going to talk about how everything in the world is at least a little bit broken. Have you ever been on a plane that was delayed because of something that seemed really stupid? Like the catch on the overhead baggage compartment was broken, and so you couldn't take off? Have you ever wondered what the overhead baggage has to do with the plane being able to go someplace? It's because all airplanes have an error budget. They have a finite percentage of things that could go wrong. An airplane is composed of hundreds of thousands of parts. And when you exceed the error budget in any way, even something stupid like a seat won't recline, then we know that it's time to take the airplane in and give it an overhaul and fix it. The same thing is true of networks. When you think about it, if you have a network that's operating at 100% capacity, what happens when you go over that 100%? It fails. So we need to be aware that full operational capacity is not actually the same as full capacity. And we need to think about that when we're calculating for how we're doing things. TCP/IP is a very old protocol, and it's built on the assumption that not all packets will get through. There's a count on the packets, and it tells you if you're missing something, and if you're missing something and it doesn't get a return, it will send it again. The whole foundation of the internet is built on the basis that things are always a little bit broken. Things are always a little bit broken. It's interesting to look at computing history and see how we're moving where we control computers. Because as we've gone through time, we've moved how it is that we think about the control surface of a computer. So here's a very brief computing history. Originally, we had hardware. We were actually touching things to make computers behave differently. We had cards. In the Apollo space program, we actually knitted beads onto wires to make the computer that helped run the capsule. That's amazing to me. Like they're physical objects that were computers that we controlled. We moved from that to machine languages, and then we realized that we could have an operating system that bundled all the ways we told machines to behave into one place, so we didn't have to keep recreating it. Anyone who's ever dealt with Linux drivers understands why this was a real advantage. As our programs got more sophisticated, we realized that we could create virtual machines. We didn't actually need to have a real port that you plugged a real cable into. We could have a virtual port, an imaginary port, that could listen for message traffic. So we decided to take a whole bunch of systems, a whole bunch of servers, and compress them onto one machine that now had the capacity to behave as if it were many machines. And from there, we realized that we didn't actually need to emulate the whole ports and drivers thing. That's ridiculous. What we just needed to be able to do was support enough of the operating system that the software would run. So we moved into containers, which allowed us to basically distribute a host operating system and the exact software we needed in a predictable way all the time, right? But it turns out that containers are not enough either. We need to be able to manage all the containers and keep them organized and make sure that they're all up, and when they fail, as they will and should, to reinstantiate another one without having to do anything dramatic. Because we've moved from the metaphor, and I don't know if this is everywhere, is we used to have servers that were pets, and they had individual names, and we knew how they behaved. And then we moved to servers as cattle, where they didn't have individual names. They still had needs, but you could manage many more of them. So this pets to cattle transition keeps going. I think of orchestration of containers as like amoebas. or bacteria. You don't care about one bacteria, but you know what to feed the bacterial colony to keep it healthy. And some of them die, and some of them are born, but it's not your problem. You're keeping the colony healthy. And now we have serverless. We're like, wait, do we really need software? Really? What if we could just perform some of these functions without needing to have all of that wrapper? When you think about how far we've come in computing history, serverless is a logical conclusion because what we're trying to do is the work, but it's also sort of a revolution to think about where the control point has moved from, how many layers of abstraction we are away from actual silicon. None of that has reduced the amount of work it takes to make things work. Everything that we take for granted, every time we use Docker, every time we spin up an operating system, someone else has done the work to make that possible. There was a really great keynote at RailsConf 2018 by DHH called Fix Me. And he talked about a concept called conceptual compression. And what it means is that lower down in the stack, things get compressed and abstracted. In order to write a web page, you don't actually need to know how TCP/IP works, or how to compile a kernel, or how to do electrical engineering. Those concepts have been compressed and presented to you as an abstraction, yeah? We end up assuming that the promises that have been made by those compressed layers will hold true. We think that because they've always worked, they will continue to work. We don't think a lot about how our actual operating system or electrical engineering or circuitry or electricity or fiber works. Some people do. Somebody in this room knows what happens when your fiber goes out, but for the most part. One example of this was Heartbleed. Heartbleed was a vulnerability that happens because chips are doing some really sophisticated thinking. They're anticipating what's going to happen, and that anticipation allows us to detect next door currents and figure things out. It's very sophisticated. The reason it was a big deal is because nobody's making their own chips. We buy our chips. They're all roughly similar. And it can affect this whole tall stack that we are sitting in the middle of, even though we have never touched the chip in question. That's pretty amazing. So we're relying on all of these promises that have been made to us. Work is neither created nor destroyed. We keep coming up with labor-saving inventions, right? For instance, the washing machine was supposed to save women all this labor because they didn't have to do laundry by hand anymore with the scrubbing and the wringer, and it was going to save them so much trouble. Well, what actually happened was we got more clothes and we started washing them more often. The amount of labor didn't change. And the amount of labor in computing doesn't change. We just don't always see it. Instead, what happens is it gets moved to other places. So instead of the problem of building a web page and remembering all that HTML and CSS, well, now you have an application where you just fill out a form and it'll build the web page for you. But who built the application? Somebody had to do the thinking to make sure that your form would work correctly and would generate valid HTML. And if you've ever used Microsoft HTML, you know that that's actually a hard problem. Technical debt is an inevitable part of our work. Technical debt is a loan that we are taking out from the future so that we can build something. It is capital that we need in order to build something. We cannot build something so good that it never has technical debt, because the very nature of building requires indebtedness. So when we think about avoiding technical debt, all we can do is make it debt that we're willing to pay off. Make the interest rate as low as possible. It's a mistake to think that the layers under us are a solved problem. Is there a less frequent problem or a less emergency? But they're still there and they still matter. And that leads to the unnerving conclusion that what we build depends on the reliability of other people. We cannot work in isolation, and we cannot assume that we're working in isolation. We have to expect that other people who are doing their best are going to fail, just like we fail. Because we are all human, and we're all fallible. Our work is compromised if anyone in our dependency stack fails to uphold the explicit and implicit promises that they've given us, right? If your Docker image is compromised, well, you should probably check for that, but there's certainly compromises that don't get published right away, and you could derive your Docker image and publish it, and you're depending on somebody else to have checked that. We're all depending on somebody else. In addition to technical debt, there's something called dark debt. And I went to a really good talk by Goldman Sachs on what dark debt is. Dark debt is debt that you do not know you are incurring, and it happens because of complexity. So dark debt is all of the weird intersections of your microservices and other people's microservices and latency and like network protocols that are almost but not quite the same. Dark debt is extremely hard to avoid and extremely hard to detect, like dark matter, and very hard to find in any way other than failure. Like the way you find out you have an edge case dark debt problem is you have an outage. And it's because not one thing went wrong and not 10 things went wrong, but 20 things went wrong. And you only have an outage in this one weird section, but it turns out that there's only one, network line in. Who knows? You could not have anticipated it because the complexity is too much for the human mind to comprehend. What we're dealing with computers is way bigger than our brains can handle. Control is an illusion. We all have to assume that we control our lives, because otherwise we'll go mad. So when we're driving, we feel like we're controlling the car, yeah? But if there is an airbag, and the airbag was installed by the car manufacturer, and the car manufacturer contracted with a third party, and the third party contracted with yet another third party to create the switch, and the switch is sensitive in the wrong way, the airbag can go off randomly and hurt us while we're driving. We're not in control. We have to assume we're in control, but we are not in control of anything in our lives. Like, our emotions are at the whim of whether we're hungry or tired or jet-lagged. Like, that day when you're just angry for no good reason? We're not in control of our feelings. We're not in control of our behavior as much as we try. And we are certainly not in control of our networks, our systems, or our software. But just like we have to try and act like professional adults when we're angry, we have to try and act as if we control our software, because it's the only way we can fulfill our promises to others. The first problem that we have is we believe if something used to work, it will continue to work. I love watching the people in the audience who were using Twitter in 2012 and know what the fail whale is. The first thing that happened when you got this is Twitter said, yo, I'm full, I can't talk to you right now, I can't even serve that request. And the first thing you would do is try again right away, because nothing makes it work like trying again. We have this belief that since it was working 2 minutes ago, it ought to be working now. But there's a lot of things that happen that make things stop working even though they used to work. And we don't plan well for that. Like, we plan okay for what if I can't get it working? What if I can't start the service? We plan less well for what if the service was working and then suddenly stops working? It's a different problem. Today's weather, which is lovely, is pretty much the same as yesterday's weather and pretty much the same as tomorrow's weather. We assume that continuous things will continue to be continuous. We know that sometimes there are storms, and we can see those coming, just like a software company knows that, on tax day, they're going to get a bunch of new signups to pay taxes, right? They know that storm is coming, they see it coming, they get ready for it, they beef up their infrastructure. It's known. But mostly, we assume that today is going to be more or less like yesterday. And that's a cognitive fallacy. If you were at the VIP dinner, we talked about cognitive fallacies. And it's going to get us in trouble because, no, it turns out things are not always the same. There will be failure. So someone gave this child ice cream, but they were smart enough to take her dress off before they did. They knew that if you give a child that age ice cream, what will happen is ice cream everywhere. So that's a predictable failure. That's a known failure mode, which is to say ice cream everywhere. And we've mitigated against it. Like, she's not going to get her dress dirty, and you can wipe her off and put the dress back on. It's all good. But if you're an adult and you're used to being, competent, and somebody hands you a glass of red wine while you're wearing a white dress, and then you're standing in a crowd and someone bumps into you, well, there's nothing you can do. And so the more control we think we have, because we're adults and because we know how to hold a wine glass, the more our accidents are surprising and damaging, because we assumed they wouldn't happen. Right? We don't know where failures are going to happen. If we knew where failures were going to happen, they wouldn't fail because we would mitigate against them. This is the Oroville Dam in California last year. This year, California is entirely on fire. Last year, it was flooding. And what happened was they got so much water that they needed to open the release chute, the overflow chute, okay? What they didn't know and had never tested, because California has been in drought for, 4 decades now, is that if you open the release valve 100%, the water will divert out of the spillway, the overflow, and carve a new creek around the spillway, because they'd never been able to test 100% water going through this, especially when the soil was wet. So the dam didn't fail, but there was downstream flooding because nobody knew that it was going to fail that way. It was not something they could have anticipated. And they can't turn off this spillway because otherwise the dam will fail and that would be much worse. So when we think about failures, we like to believe that we can mitigate them because we know where to expect them. Like, oh, we know that server is flaky, we're going to take care of that. But the truth is, you don't. You don't know where it's going to fail. So what are we going to do about the fact that humans are fallible and software is fallible and networks are fallible and everything's terrible? I have some good news. I have some ideas for you. How to handle this constant state of everything being a little bit broken. Error budgets and harm mitigation. Error budgets are the idea that you get a percentage of things that can be wrong without people yelling at you. Because like networks, trying to hit 100% capacity and 100% perfection just means that your failures will be catastrophic instead of minor. So adding an error budget, we call them service level agreement and service level, what's SLO? Thank you. So we're saying, like, we guarantee to deliver this 98% of the time. 2% of the time, we might need an outage, we might have gone down, whatever. I need you to not count on me 100%. Right? Make sure, and then harm mitigation is acknowledging that things are going to go wrong and making sure that when they do, it's not catastrophic. We'll get into that in a minute. So for an error budget, you have to decide how much failure is tolerable. How much failure can you take before it becomes a business impact? Because really, it doesn't matter how much the server goes down if the users never notice. The problem is when whoever your user is notices, then you have a problem, and you have to work backward from that. So if you could keep your servers up full-time with like balloons flying over users' houses, that'd be great. That's all you would need. But it's hard to do that. The balloons get hit by lightning and stuff. So what we need to do instead is figure out how to make sure the users are not affected by our problems. Reduce catastrophes. So the difference between a failure and a catastrophe is cascade. A failure is one point. A failure is one thing going wrong. A catastrophe is when everything goes wrong, when that one thing kicks off a bunch of debt that you didn't know you had, it kicks off a bunch of problems, and you end up with this total outage because you hadn't managed to isolate what's going on. So, for example, when the Challenger explosion happened, this is the case that they make us read in business school. Challenger had a faulty O-ring, but it wasn't really faulty. It was just bad at low temperature. And we knew that. Some people knew that. But they didn't manage to notify enough people up the chain to say, like, this could lose containment, we could have a fuel leak, it could be explosive. It wasn't just one thing that went wrong. And every disaster report you look at, it's not one thing that went wrong. It was like, this thing went wrong, and that threw extra load on this part of the building, and that part of the building wasn't designed for extra load, and so it crumpled. Right? When you read this, I like writing disaster reports because that's the kind of person I am. Many DevOps people do. I think we all love the like terrible stories. It makes us feel better about our lives. So when you're thinking about disaster, you have to make sure that you're isolating things and putting in circuit breakers so that if something goes wrong, it won't cascade. Like, the reason we have circuit breakers is because humans are slow and made of meat, and we can't pull the fork out of the socket. I wonder if that works here. Your sockets don't work the same way. Yeah, anyway, we can't break the circuit fast enough to avoid getting killed, right? So we put in circuit breakers so humans didn't get killed, and so that if we overloaded the system, it would fail safely instead of failing with fire. Every time you put in a circuit breaker pattern, you're saying, I don't think this is going to fail. Like, probably you'll continue serving for like years and nothing will happen. But if something does happen, I don't want it to keep going. So isolating each element of your system so that you can turn it off and it doesn't spew garbage to the rest of your system is really important. And you want to have control points. You want to be able to say, I'm going to turn this down because it's too noisy. It's sending too many log reports. Or I'm going to turn this up because I need to know what's going on. I want to see those log reports. Having control points at different parts of your system mean that you're not overwhelmed. You want to have rapid rollback. Are you not going to give me that slide? There we go. You want to have rapid rollback. We talked about that in the keynote this morning. You want to be able to make sure that things are not out there being wrong for a long period of time. One of the ways we do this is we put kill switches on features. So When we deploy them, we can roll them out slowly and gradually, do progressive deployment, but also if they go bad, we can turn them off right away without having to do another deployment, because doing a deployment is always dangerous. That's why we used to do them at outage windows. And so if you have an emergency and you need to do a deployment, the chances are you're going to screw it up somehow. Make it so that you can turn off what's bad without having to do a redeployment. Add layered access. Oh, I just totally lost my... Add layered access to your system. You want to make sure that people are getting the results that they want when they want it, but you don't want to let the intern put anything in production, because that's just going to end poorly for everybody. It's fine. I will tweet the slides after the talk. So you don't want anything to have direct access. You're trying to do microservices, you're trying to do loosely coupled architecture, right? Nothing should write to each other. It should all be mediated by APIs, because if you have things writing to each other, then they can get in a terrible feedback loop, and that's a real problem. You want to make sure that you have authorized users making changes, and you want to use abstractions to manage change. An abstraction layer allows you to say, hey, I'm calling for this kind of data, and the service can provide that kind of data no matter what it is. If you change a database, it should not change your call into the database, because you should have an abstraction layer in there, right? So when you're building software, I want you to assume that there will be breakage, and I want you to mitigate that by adding isolations and circuit breakers. I want you to build supports for weak spots that you've found out the hard way need to be shored up, because it's not pretty, but eventually you will build a whole new structure of all of the weakest spots that have been secured. Remember that everyone's back end is someone else's front end. When you think of front end, When you think of front end, you're probably thinking about your console for your DevOps things, but that's really the back end for your application developers. The application is the back end for the designers. The design is the back end for the users. Like, everybody up and down the stack believes that they are roughly in the middle, and that's not exactly true. So if this talk was too long or too English and you read Twitter instead, here's what I want you to remember. Depend on nothing. Use it, but don't depend on it. Assume people will do the best that they can, and prepare for failure. And if you would like more information on how to do isolation, circuit breakers, control points, I work for a company called LaunchDarkly. You can take a picture of this slide. We will send you a 30-day trial and a free t-shirt. Thank you all.